The law of conservation of mass states that atoms, or matter, is neither created nor destroyed. It just simply transforms into something else. We balance chemical equations to demonstrate this concept of law of conservation of mass. When we demonstrate the law of conservation of mass by balancing chemical equations, we show that atoms, specific elements, what goes into the reaction, also must come out, and it's usually transformed into something new. But all of the same atoms are still there. So how do we do this? What are some steps that I could give you to help you balance chemical equations? So I follow a pattern of 5 easy steps to balance a chemical equation. And I'm going to do a couple of different examples from the different types of reactions for you to kind of show you my strategy behind each type of reaction. But the first thing you need to do is you need to count the atoms on one side of the actual arrow, the reaction arrow. And then 2, count the atoms on both sides to see what's missing. You're trying to figure out what elements are missing on the left side of the arrow and the right side of the arrow. 3, you're going to add coefficients to make the numbers equal. That's the part that sounds a little bit easier than it really is. And then if there's a reducing situation that's necessary, then you reduce to get the lowest possible ratio. And then always, always, always go back and double check it. And I will go through this with you. I have some helpful hints and tips for when you're balancing chemical equations. Just a couple of helpful hints. Never change subscripts. It's going to be very tempting, but don't do that. I follow a procedure that is count, adjust, check. Count, adjust, check. That's just how my mind operates and how I balance equations. A lot of times, if you're a little math savvy, you can use decimals or fractions to help. However, you feel more comfortable with that, and you'll see me do that too. I'll show you that strategy. And then, for the most part, you just treat polyatomic ions like they're a single element. They are on a list for a reason. They hang out together, and so you can just basically treat them like, like eggs. So let me just show you what I mean by balancing an equation. So here I have aluminum plus um, nitrogen gas, and it's going to make aluminum nitride right here. So when I look at this, there's one aluminum over here and one nitrogen. There's one aluminum there and 2 nitrogen. Now that subscript, that's what I mean. You can never, never change the subscripts. All you can do is add numbers in front of the compounds called coefficients, and to get them to equal the left side of the arrow and the right side of the arrow. So if I have one aluminum and one on the left side and one aluminum on the right, those are the same. But my problem is nitrogen. I have 2 on the left and 2 on the right. So I'm going to put a 2 there. I know I need at least a 2 in that place. Now that coefficient, when I have something like 2ALN here, that 2 is distributed amongst everybody in the compound. So that means I've got 2 aluminum and 2 nitrogen. So now my nitrogen balance, because I've got 2 here and I've got 2 here, but my aluminums do not. So I'm going to put a 2 right there. So that gives me a 2 aluminum plus N2, 2 nitrogen, and 2 ALN. Now, while you're learning, you can put a 1 there. But what this really tells us is that we have a 2 to 1 to 2 ratio. This is basically a ratio. It means that it takes 2 aluminums atoms and 1 N2 molecule to make 2 ALN aluminum nitride molecules. That's what it means. Okay, let's do some more practice. Okay, so when you're using polyatomic ions in your equation, like here I have a double replacement, you can see how this NO3 and this NO3, this nitrite is this, it's the same on both sides of the reaction because it doesn't change. So I just treat it as if it's an element, just right there. It helps keep me from counting all of these nitrogens and oxygens and distributing. Here I have CrO4, like that is also a polyatomic ion. I can just treat that as if it's its own element. And then all of a sudden, PbxK2y make PbyKx is a lot more simpler to balance. Alright, so let's try this. I've got one lead on the left side and one lead on the right, one X on the left and one X on the right, two potassiums on the left and one on the right, so I know I need at least a 2 there. And then I've got one Y and one Y. So when I look at it, this is balanced. This is a 1 to 1 to 1 to 2 ratio. So when I erase all of everything I've written all over, you can see that this means that I have 2 of these potassium nitrates. And if you look over here, there's that little 2 that's distributed. So that makes sense, right? Because there's 2 groups of NO3, and now I've got 2 groups of NO3 over there. All right, let's try another one. Silver nitrate plus sodium hydroxide make sodium nitrate and silver hydroxide. So again, if I have NO3 right here and my OH, which is also a polyatomic ion, now all of a sudden it looks very simple to balance. In fact, one silver, one X, one sodium, one OH, one OH. This is actually a balanced, this chemical reaction is what we call a balanced reaction, a 1 to 1 to 1 to 1 ratio there. All right, let's try this. This is a little harder. And these polyatomic ions can be a little more challenging to spot, but there's one. That's the anion. And the other one is right here. Okay, and then something's happening with my hydrogens and oxygens there. Okay, so if I look on the, if I'm dividing the chemical reaction right here, I want all of my sodiums, hydrogens, sulfurs, chlorines, oxygens on the left side to equal all of those on the right. And that's a lot of elements to sit here and draw and count individually. That's why it's important to have a strategy when you're balancing chemical reactions. Okay, so I have a Y on the left and a Y on the right, an X on the left and an X on the right, and it looks like my hydrogens are split up here. But if I look, I've got 2 hydrogens and 2 oxygens over here, and I have 1 oxygen and 2 hydrogens on this side. So again, this reaction is actually balanced because what we want is the actual elements, hydrogens and oxygens and nitrogens on the left side to equal that on the right. So we have another balanced reaction at 1 to 1 to 1 to 1 ratio. Okay, what if I have a split term, which is often the case in a combustion type of reaction? So now I'm going to use some of my math savviness, some of my math strategies, and I'm going to use decimals and fractions. Okay, so here I have, on this side, I have iron hydroxide, and it's going to decompose, because this is a decomposition reaction, into iron 3 hydroxide and water. Alright, so I like to do just the metal first when I see something like this. There's usually some sort of metal, transition metal that stands out. So I have 2 irons over here, so I need at least 2 over there. And on this side, I have oxygens are 3 and hydrogens are 3. When I put a 2 there, I've made them 6 and 6. So when I look at my hydrogens and oxygens on this side, I have oxygen that's split, hence the name split term. So I'm going to do the hydrogen first and then deal with that oxygen. I have 6 hydrogens on the left side, so I want 6 on the right. So 2 times 3 would give me 6. And so now I'm going to look at this oxygen. I have 3 oxygens right here, and I have 3 right here. And, well, that's what I'm looking for, right? Because I want 6 overall. So my oxygens are split, but in this instance they balance. So I have a 2 to 1 to 3 ratio. All right, here's my next one. This is a hydrocarbon, dicarbon tetrahydride plus oxygen makes CO2 and water. That's a combustion reaction. So there's no metal that sticks out here, so I'm going to start with carbon. I've got 2 carbon on this side of the arrow, and so I know I need at least a 2 there. I have 4 hydrogen over here, so I know I need at least a 2 there. And I could always go back and adjust those 2's, they're not permanent. So now how many oxygens do I have? I've got 2 times 2, there's 4 oxygens there, and 2 times 1, there's 2 oxygens there. So I have 6 oxygens total on this side, and over here I have 2. So if I put a 3 there, then my oxygens should balance. What's on this side of the arrow is now equal to that side of the arrow, and I've got a 1 to 3 to 2 to 2 ratio. All right, this one looks a little harder. This is C4H8 plus oxygen make carbon dioxide and water. So if I've got 4 carbon on this side of the arrow, I know I need at least a 4 there. And next I'm going to do hydrogen. If I've got 8 there, I'm going to put at least a 4 there. All right. So now let's look at my oxygens. Over here I have 4 times 2, that's 8 oxygens, and then that's 4. So 4 plus 8 is now I have 12 oxygens. And if I look over here, I need to make that a 12, so I'm going to put a 6. So I have a 1 to 6 to 4 to 4 ratio on this split term. I didn't have to use any decimals and fractions here, but I'm going to get to that and showing you how to do that too. It would be like if this was an odd number. Like what if I've gotten 15 oxygens over here? There's nothing that you can put in front of that 2 to make it a 15. So you would have to use a decimal and then multiply everybody across. And I'll explain that here in a bit. Okay, so now on to split terms that might have an odd number. And how do I do that? Oops, sorry there. How do I do that is, use decimals, fractions, and then multiply. Oh my! Here I have a combustion reaction where I have 3 carbons, so I need, we're getting into odd numbers already, 3 carbons on that side. I have 6 hydrogens over here, so I'm going to put a 3 there. That's a 3, to make that 6 over there. So now let's look at my oxygens. I have 3 times 2, that's 6 oxygens there, and 3 there. So that gives me 9 oxygens total on the right side, so I need 9 over here. Well, what can I multiply 2 by to get 9? And the answer is, well, nothing. Well, at least not a whole number. I can multiply it by 4.5, right? If you put this in your calculator, 2 times 4.5, you're going to get 9. So 2 times 4.5 equals 9. So I'm going to put a 4.5 there. Okay, technically this is balanced. And if you were in college, we really wouldn't go any further because all we need out of a balanced reaction to do any math is the ratio. And you do have a 1 to 4.5 to 3 to 3 ratio. And if you know much about ratios, the next part really doesn't matter. But we want to make sure that it looks pretty. So how do I make all of these coefficients right here, these numbers in blue, how do I make them all so that they are whole numbers? And the answer is that you go in and you multiply everybody by 2 to make them whole numbers. So this is 2 times 1, and that's going to give me a 2. Oops, there you go, 2. 4.5 times 2 is going to give me 9. 3 times 2 is going to give me 6, and this is going to give me 6. So I have a 2 to 9 to 6 to 6 ratio. And if you were to double check, that's your balancing on both sides, you would see I have 6 carbons there, 6 carbons there, 12 hydrogens right here, and so I have 12 hydrogens right there, and then 9 times 2 is 18 oxygens, and then on this side I have I have 12 plus 6 oxygens, and that's also 18 oxygens, so that's balanced, and that's your ratio. All right, let's try another one. I've got 4 carbons over here, so I'm going to put at least a 4 there. 9 hydrogens. What can I put in front of that 2 to make it 9? 4.5. See, at this point, there's no point in continuing to add whole numbers until you get all the way up there. I mean, you could do it just like all of the other ones, but if you use fractions or decimals, it just makes it go by a little quicker. All right, so now I've got 9 hydrogens on both sides. Let's look at my oxygens. I've got 4 times 2, I've got 8 oxygens there, and 4.5 times, 4.5 oxygens there. So this is 8, 9, 10, 11, 12. I've got 12.5 oxygens. What can I put there to give me 12.5 oxygens? And the answer is 6.25. Okay? So when I have a 1 to 6.25 to 4 to 4.5 ratio, all of my stuff is balanced. But I can't leave it like that. I have to go in and multiply everybody to get a whole number. This time, I just can't go in and multiply everybody by 2. I've got to do something else because if I multiply this guy by 2, I'm still at, 12 and a half. So I'm going to up that and multiply everybody by 4 because that will at least take care of this quarter part here. And let me see how that works. So if I go through and I multiply everybody by 4, I get 4 here. And then 6.25 times 4 is 25. 4 times 4 is 16. And 4 times 4.5 is 18. All right? It's getting kind of hard to see. So let me see if that works here. All right, so let's double check our carbons. 4 times 4 is 16. 16 times 1, technically there is 16 carbons. And so 9 hydrogens, so the hydrogens balance. I know the oxygens balance. Okay, so now this is balanced. And this is a big number. And guys, this is really about as hard as it's going to get. Okay, so I'm glad I'm doing one like this with you. So in this instance, I have a 4 to 25 to 16 to 18 ratio for that problem. All right, let's try one more. Here I have 10 carbons. Change my color. So I'm going to put a 10 there, giving me 10 carbons. 22 hydrogens, so I'm going to put an 11 there. And now let's work on those oxygens. I like how at least the oxygen is just right there. All right, so I've got 20 oxygens right there. 2 times 10 is 20, and 11 there. So 20 plus 11 gives me 31 oxygens on this side. So 2 times what is going to give me 31? Do you know? At this point, if you don't understand how to do that, you could also take 31 and divide it by 2, and that would give you your answer, right? Let's do some algebra. Let's divide by 2, divide by 2. That makes my question mark is going to equal 15.5. So 15.5. All right, I know I can't leave it like that, but the good news is that I'm at a 0.5, so I just want to multiply everybody by 2. 1 times 2 is 2. Keep doing that. 15.5 times 2 is 30. 31. 2 times 10 is 20, and 2 times 11 is 22. So I have a 2 to 31 to 20 to 22 ratio on that one. And this is just another one of those things where don't practice until you get it right. You practice until you cannot get it wrong.